later. For now, let us sharpen our ears and give him our time. Thank you.
Good morning, everyone.
Good morning.
I'm happy to be here to share with the work we are doing in Zambia at Even On College. Thank you very much. So at Even On College in Zambia, we came up with this proposal, a tether fluoride convolution neural network model for cardiac sound classification. So this paper is based on a project which we are working on, development of digital stethoscope. Next slide. So I'll go through the background, methodology, results, conclusion, and acknowledgements. Next slide. So cardiovascular diseases is one of the leading causes of death globally. So we're talking about 17.9 million people die each year from cardiovascular diseases, estimated of 32% of death worldwide. So over 75% of cardiovascular death in low and middle income regions. The diagnosis of cardiovascular disease by auscultation using a stethoscope require experienced doctors and their experts. So in many developing countries like Zambia, we have a low doctor to patient ratio, about 1 to 12,000, and one doctor almost attending to 12,000 patients. So looking at this problem, what did we propose? So we proposed a need for computer-aided tools to assist for cardiovascular disease diagnosis. So this study presents a convolutional neural network model for cardiac sound classification. So here's the method. So we have data waveform database. We have PCD, phonocardiography signals, the stages pre-processing, feature extraction, and classification at last, where now the artificial intelligence model will decide to say, oh, this is abnormal, this is normal. So in the next slides, I'll go through what's happening at waveform database, at pre-processing, feature extraction, and classification stage. So we have a database of a phonocardiograph database. So we adopted a data set from Physionet Computing Cardiology Challenge was in 2016. So 3,126 cardiography signals were collected from different parts, like from the aortic area, harmonic area, tricuspid area, and meet about at a length of 5 to 120 seconds and sampling rate at 16 kilohertz. So these are 3,126 phonocardiography signals. There are about two classes. So we have abnormal and abnormal sounds of the heart. So for us to work with these signals, we have to split. We have to split these signals into training sets of 80% and validation for 20%. So now, here we are, the processing and feature extraction. So looking at time domain there, we have a Butterworth with order bandpass filter 22 458. So what is happening there? So these phonocardiograph signals, when we were being collected, there are other signals which were also captured. So we are not really interested in some of these signals. For example, I can give lung sounds. So we're not interested in the lung sound and other sounds. So we have to introduce a Butterworth order bandpass filter 20 to 450 Hz. So it will cut off every frequency that is out of that range, 20 to 450 Hz. It will cut off any frequencies in that range. So from that, we go to downsampling. So downsampling, the original signal was acquired at the 16 kilohertz. Now, for us to work with it in a machine learning model, we have to downsize it to a level where it will be able to, for it to be workable. Downsampling. I can give an example of. A burger. You order a burger. It's so much big. So, like for you to buy it from top to bottom, you have to squeeze it so at least you can have a bite. So it's what was happening. It remains, even though you squeeze it, it still remains a burger for you to be able to eat. So it's what was happening here, downsampling to 2 kilohertz. Now, when we do that, we come to frequency domain. So what is it happening in that frequency domain? So we have to calculate short time fast Fourier transform. We want to know what is really happening at each given time. What is happening to the frequency at each given time? So when that is done, we come to MCC, male frequency perceptron coefficients. When that is we will come to that part. Now we can calculate. We have a function there. We calculate what we call the male spectrogram, the picture there. So for convolutional neural network, for it to work, we have to work with the male spectrogram. So now, on that part, those signals have been presented in form of an image, So what you see, you have got lighter parts, darker parts. So when the lighter parts, those are coefficients. So convolutional neural network model will be able to be so much easy for processing this picture. So when we come to convolutional neural network model architecture, what will be happening now? So we have input layer, we have convolutional layer, and we also dense layer and the output layer. So on the input layer, we have 120 features. So 120 features, they are coming from MFCC. That's where they are coming from, 120. So what was really happening, a convolutional neural network model was able to pick from the pictures, trying to interpret